on.
We're good.
Okay. My name is Julia Kuznetsova. I work for Advanced Auto Parts, and the first thing I wanted to say is thank you for having me here. I actually did not realize that I'm going to the Duke Blue-Green building, so I'm actually fascinated that I'm presenting in the Duke Green building. The other thing I wanted to say is thank you for getting me the cable. It looked like that was quite an adventure. For those who were not present for the adventure, my laptop turned out to be extremely outdated, and we did not have the correct cable for HDMI to connect to it. And the two very nice, helpful gentlemen disconnected something from somewhere in order to help me.
It's just a main server that runs the hospital.
Okay, now that we've discussed everything important, let's get to my presentation. And I'm going to talk about a story that actually happened at Advanced Auto Parts, where we have a sales forecast. As you can imagine, that's very important. We are a large chain. Oh, for those of you who don't know, we are a large chain of stores, and it's important for us to have a sales forecast. And our sales forecast was running on an extremely old legacy system. For those who know it, it was SPSS 15. So we decided that it's time to replace it. And in replacing that, we also decided that we would like to replace what that forecast is predicting. So the old forecast was predicting probability to sell, and the new forecast is predicting quantity, like quantity, how many items will be sold. And I will talk about why we decided to do that. But as you probably can imagine, when you're replacing one forecast with another forecast, you would like to prove that your new forecast is better, or at least not worse than your old forecast. And usually it's pretty standard procedure. You choose a metric, something like mean absolute error, mean absolute percent error. You compare those errors. Sometimes you do like group by, compare for different groups. You show that this is slightly better, maybe a lot better, and you proceed. In our case, that was not possible to do because we had very different things on one side and on the other side. So this is the story about how we did compare those two very different things, which I called apples and oranges in this presentation. Okay. So first, I will talk about what actually those two forecasts predict and what do they do, because that's important for understanding how we did that comparison. Then I will discuss actually our way to compare two forecasts with different values, the accuracy metric that we created. We'll talk about subsetting data for comparison. And I will also talk about interpreting the results, because it turned out that for this particular method, it's unclear how to do that. And there is an interesting story about that. So first, okay, we are a chain of stores, which usually look like that. There is one very close to here in Chapel Hill. We sell auto parts. And what is interesting about selling auto parts, that among different retail markets, we have very low turnover. And the turnover for auto parts aftermarket is 0.3. And in order to give you a point of comparison for the grocery store, the turnover is 14. So that turnover means like how often the products that are on your shelf are completely changing. And this means that for a normal grocery store, something that would be sold once a year would never appear on their shelf. They would be like considered completely not interesting for their business. However, for an auto parts store, that is actually a very interesting item. We'll keep that. Another interesting aspect of predicting auto parts sales is unique fit. So if we were a shoe store, we would be in business of selling glass slippers, because every person who's coming and telling us, I have a Nissan Rogue 2016, I need a water pump. And we enter that, and probably there will be one item in the store that fits that. So it's pretty unique fit for our customer. So given all that, as you can see, that store is not extremely large. So we cannot fit everything into that store. So we have to come up with very optimal assortment. What should be in that particular store in Chapel Hill that is responding to the needs of the customers nearby. So this is exactly what we're doing. So first, we're forecasting, and we're forecasting for every part, every store. And when we were forecasting probability to sell, we would come up with a number. So that would be in the next year, probability to sell this particular part, that particular store, is, say, 0.8. That's a pretty good number. Probably should put that in. When you have your items, and in this particular extremely simplistic case, you have items of exactly the same size. That's usually not the case, you can imagine. And your sizes, for this particular very simplistic case, there are only two sizes. They exactly fit our items. So we have A, B, and C. Probability to sell them is 0.8, 0.7, 0.5. We have only two spaces, so our assortment says, okay, I'm choosing the two items which have highest probability to sell. So A and B go on the shelf, C is not there. Yes?
So I'm curious, right? The size in inches makes sense, right? You only have so much shelf space.
Yes.
But if one of them makes you $1,000 and the other makes you 10.
I'm sorry?
If one of them makes you $1,000 and the other makes you 10, there's a value component.
Yes, this is why I'm saying this is very simplistic example. This very simplistic example, yes, only looks at the forecast and only at the space constraints. Of course, there are other constraints and other things that go into this assortment. This is just very simplistic to just explain how it works. Yes?
The probability to sell is over each individual fiscal year, calendar year, 2 years, or the probability that it would be sold at all?
It was probability to be sold in a rolling year. So if I would be making that prediction on August 27th, 2019, that would be probability to sell from this day until August 27th, 2020.
Okay,
Rolling year. Okay. Anything else? Okay. If I'm predicting quantities, then again, for every part and every store, I'm trying to forecast for exactly the same rolling year how many units I'm gonna sell at that particular store of that particular item. And again, the assortment in this case works pretty similar. So it says, okay, I have something that will be sold 5 units, that goes on, 2 units, that goes on the shelf, 1 is not going there. That's it. Another interesting part about forecasting order bars, like we discussed that we are interested in lower, like small, not so fast selling items. That means that our forecast has to be really good for small things. So for something that is predicted to be sold like 100 units, there is no question. It goes on the shelf immediately. We're not discussing it. And if there is a question between 100 and 90, it's not that important because it goes on the shelf anyway. Where we have to be very good is like the lowest end. We have to predict twos, threes, twos, ones, and zeros really well. Okay, so this is again extremely simplified. In reality, this table is much wider and of course much longer. But this is an example of how this can be predicted and how this looks like. So we have a part in a store, we have a part type, we have fuel filters and oil filters. We know how many items were sold last year. We know how many cars are in the area that actually that part fits that vehicle. We know how long that particular item have been, where they are in their life cycle. Is this just a new item, or is it that's the item that just fits the old vehicles, so it's going out of their life cycle? We know what kind of area type is there, and for probability predictions, we were looking at a column which was it sold this year? And for units, we are interested in the column how many units we sold. And then we're taking the predictors, and for probabilities, we're taking this column, and for quantities, we're taking that column in order to predict what's going on.
Julie, what are cars in the area? Your metal cut, your...
So for each store, we know how many cars surrounding that store use that particular part.
So you have access to DMV records?
Sorry?
Like DMV records? You have DMV records?
We are purchasing that from a third-party company, which purchasing DMV data, aggregates and de-anonymizes it. Or no, anonymizes it. Sorry. Thank you. Yes, and then like aggregates that to large geographical areas. So yes, we don't know anything particularly about you personally, but we know what's going on in Chapel Hill. Okay, so when then we are going through the standard procedure. We train our model using the past year data. Then we have that model, and we can compare the predictions from that model using the current year data, because we know what's the current year data. And then we use the model that we've created, and we believe that this is a good model in order to predict future year sales from the current year. Okay. Now that we've discussed what those forecasts are doing, immediate question, why did we decide to make that change? Because it was, of course, much easier not to do it. And one issue with having forecast which predicts probabilities is that it, of course, works for creating assortment. It does not work for creating replenishment. So replenishment is like how many units do we need in our store? Because for something you might need 2, for something you might need 5. Your probability to sell only tells you, yes, that should be at the store. No, that should not be at the store. It does not tell you how many units you should put on the shelf. And in order to still know how many units should be there, you need to have additional forecast, which gives you units. If you create units, you can run both your assortment and replenishment on the same forecast. So that was unification. Another issue with probabilities was that our users, people who actually worked with the stores, frequently told us that we're not sure what probability to sell 0.5 actually is. And we try to tell them that probability to sell 0.5 means that most likely in 2 years that item will be sold. It's actually not exactly true, because that would be true if those two events would be independent. Of course, selling something in this year and selling something in the year after that is not independent. So we kind of thought that there is something about that psychologically not extremely clear metric. And we understand that it is also would make it much easier for the end users if we switch to quantities. And then when they heard that, they said, yes, quantities we understand. Okay. Okay, so this was our goal. So we've created 2 models. One was model with probabilities. One was model with quantities. We had the data, so they both produced forecast for the current year, for which we already knew the actual data, actual sales. So we can compare. The only question is, how do we compare now probabilities and quantities? And what we came up with is that, of course, you cannot compare probability to quantity, but what you can do is you can compare 2 probabilities. So if you have 2 part store items, part store pairs, you can say that, okay, number 1 probability is 0.04, number 2 probability is 0.06, so this one is bigger than the other. We are predicting that this is more likely to be sold. And for that exactly same pair of part and store, we can also look at their quantities. We can say, okay, for the number 1, we're predicting quantities 1. For number 1, we're predicting quantities 2. And one of them is bigger than the other. And their relationship is what is important for assortment, because remember, our goal is assortment. And actually, their relative comparison is what's important here. And what is important, again, we also have the true data, sales. And sales also tell us, okay, for part 1, store 1, there are 0 sales. For part 2, store 2, there are 2 sales. So sales also actually are ordered for pairs of parts and stores. And here I ran out of preferable fruits, so I added watermelons.
I want to make sure I follow this. So are you basically saying that you use both of them to choose assortment? And once you chose assortment, you looked at which ones
Nope.
got assortment right most often?
Nope. We just used them to create orders of part store pairs. So each part store pair was compared to another part store pair, because for each, for probability forecast, for quantity forecast, and for actual sales, you can rank them. Either one's.
So either A is more likely to sell, or A will sell more, counted the same.
Yeah, exactly. And actual sales also tell you either A sold more or B sold more. So it was possible to rank all of them. And after we ranked them, then it was possible to compare them to each other. However, we immediately ran into a problem. And the problem was that, okay, if we are comparing 10 to 100, it's pretty clear that one is smaller than the other. And if we're comparing 100 is also more than 10, what about 1 and 3? Probably 1 is still smaller than 3. We talked about the differences between 1 and 3 are probably most important. What about 98 and 100? This is these are probably pretty close, maybe exactly the same, even though the difference is the same as between 1 and 3. Same probably goes for 900 and 1,000, or what about 0.3 and 0.7? Because you're predicting quantities, sometimes they're not integers. So we had to come up with thresholds. So what we said was, okay, for items which are below 1, we will use 0.5 as a threshold because we remember that we are talking about actual units which will be sold. So it will not be possible to sell 0.7 units and 0.3 units, so we'll probably 0.7 will be rounded up to 1, 0.3 will be rounded down to 0. So the threshold there would be 0.5, something that's is different. If the difference is bigger than 0.5, then they're different. If it is smaller, they're the same.
Basically did 10% error with the high end.
Yes, after that we did 10% error and just rounded it a little, yes. So that was just our decision based on mostly experience of people who deal with assortments. And for probabilities, we also did the we did the 0.05 threshold, just because for probabilities, that's usually a threshold that is used for significance. But again, that was just our decision here. Okay, now that we have method to compare them and our thresholds, we can create, like each of those can create a vote. And vote can be less, more, or equal. So we have peer 1. For peer 1, probability is 0.74. First probability is 0.74. Second probability 0.76. So since that is smaller than our difference between them is smaller than our threshold, the probability vote is equal. So probabilities, we're saying that is pretty close. We say that they're the same. Quantity is 12 for the first one and 14 for the second one. Again, that's within our threshold. We're saying that's the same. And the sales in this case were 12 for the first case, 16 for the second case. So the sale vote is actually, so that is bigger than our threshold. So the sale vote here is less. The second one, we see that probability is 0.74, second probability is 0.8. So now their difference is bigger than the threshold, so the probability vote is less. Quantities here are 14 and 16, so difference between them is 2, so they're within the threshold, so quantity vote is equal. And sales are 16 and 14, again they are within 2, so sales vote is equal. On the final row, here we have probability 0.76 and 0.8. Again, that's within the threshold. The probability vote is equal. Quantities are 12 and 16. Difference is higher than the threshold, so the quantity vote is less. And sales at 12 and 14. Here they are within the threshold. The sale vote is equal. Does that make sense? Okay. So now probabilities, quantities, and actual sales all have equal, less, or more column. And now we can compare, because they are pretty comparable. We can just count how often that matches. So we can compare probability vote to sale vote, which is the truth. We can say, okay, first one not equal, second not equal, last one equal, so we are calling that a concordant peer. Concordant peer is then our votes are equal. Oh, I actually did that. I forgot about that. And now we can also compare the quantity vote, and the quantity vote would be the first one is not concordant, second one is concordant, both equal, and the last one is not concordant. Now we can just calculate the percent of concordant peers. Of course, we run into another problem, which is, remember, we took part and store, and we multiplied parts and stores with parts and stores. That creates Cartesian products of store-part combinations. So in case you had 20,000 records, that means you're not taking the ones which are repeating itself, but still you would have 20,000 multiplied by 20,000 divided by 2 because you don't want the repeating ones, minus 20,000 because you don't want the diagonal one, but still you end up with about 200,000 records, 200 million records, thank you, which is a lot. So what we did, we said, okay, we probably don't need to compare everything with everything because our part types are not, like our brake pads are not competing with radiators for the space. We store them in different locations at the store. So we're probably okay if we just compare how our radiators are comparing within each other and how our brake pads are comparing within each other. And we will be fine because they are not, different part types do not compete with each other. Yes?
So did you look at, in this case, electrical system, cooling system, transmission system, and do a categorical comparison, or did you find it that you really needed to drill down into the spark plug v spark plug and radiator v radiator and brake pad v brake pad?
We ended up doing like part type. Everything in our system is classified into part types, and part types are pretty specific. So spark plugs would be part type.
Okay.
Um,
Because I mean, you can do.
It still did not solve our problems because, of course, we had some part types for which we had kind of a small number of records, and we still have part types for which we had very large number of records. 20,000 appears here not by chance, but because that particular system on which we were running this analysis had that as the largest round number for which it can do that Cartesian product analysis. So we said, okay, 20,000 is probably a pretty big number. So for those part types which are under 20,000, we'll take the whole thing. For those which are bigger than 20,000, we'll just take a random sample of 20,000 and we'll just run with it. Okay. So now we're done with the metric, done with how the comparison is done. We can look at the results of the comparison. So this is what the analysis looked like. We did this on the sample of 217 part types. And the number you see here is percent of concordant peers. So out of all part store peers, how many were concordant with the actual sales?
How did you deal with the fact that in order for storing of the metric means you had to have sold it, which means it had to have been available in the store? What about the parts that are sitting in a warehouse that have never been in the store, but maybe they should be? How did you figure that out?
Remember that our analysis, our forecast has to be tied really well in that particular area, so it has to predict zeros and non-zeros really well. So we had to check that. Okay, so as you can see here, quantity is doing pretty good job here. It was actually doing pretty good job all over the place. However, I promised you an interesting interpretation story. There was a person who looked at that data, and of course I did not show you the whole table. The whole table is 217 part types down. And there was a person who looked at that data and decided to summarize it. And that person said, quantity forecast is on average 11% better than probability forecast. And you can kind of probably follow the thinking behind this. So, okay, we've got number on the left column, it's a percent. Number on the right column, it's a percent. Okay, we can take a difference. So if we have 85 here and 60 here, okay, if there's 25% here, we can probably even interpret that. We can say, okay, quantity forecast was correct and 25% more peers. Okay, that still works. After that, you have a column with difference, and it's very compelling to take an average of that.
Danger, Will Robinson.
4 million actuator valves.
Yes, you've already, yes, found out what was the problem. And yes, I just told you that some of those parts were smaller than 2,000 records, and some of them were much bigger than 2,000 records. They were not balanced at all. So what I would like to argue here is the way you summarize the data needs to be consistent with the goal of the analysis. And the goal here is to test whether one forecast is more adequate than the other forecast for the purposes of assortment. And one forecast can be on average 11% better than the other, but still inadequate for assortment. And here is an example of such forecast. So let's say that in this imaginary scenario, we have 7 part types, and the differences between them are 44 and 55, just to make it always 11 difference. So the difference in the first 4 will be 11. Difference for the last 3 will be minus 11. And the average of that is 11. However, let's imagine that the first 4 have 1 record, and the last 3 have 1,000 records. And when we look at that, and we're saying no, even though it's on average 11% better, we are not going with that forecast, no. What could be done there? So we tested that on 217 part types. And we are interested in the case where the accuracy or percent of concordant peers is higher for quantity forecast as compared to probability. And it was for 215 part types out of 217, which we decided was pretty good case and have replaced our probability forecast with the quantity forecast.
So for those other 2 that it wasn't better, were you able to tweak your algorithm or do something that would say, we're going to do these 2 by hand?
No. We decided that the majority is good enough. Explore them and looked at the ways to make the forecast better for them, but no, we do not do assortment by hand. That's very dangerous. Okay, so I hope that I showed you that there is a way to compare forecasts which predict extremely different values, probabilities, and quantities, and showed you that one way to do that is to use concordant peers, which allow you to compare votes for your 2 different forecasts, and that vote can be compared with the truth vote. which allows you to measure accuracy as concordance of forecast vote and sales vote. The interesting thought behind this is that the thing that allowed us to do this is because we are using this for assortment, which means that relative ordering of peers is the only thing that is important for us. If our use case was different, this could have not worked for us.
You had to do this for each store separately.
Sorry?
You had to do this for each store separately.
No, we did that with like large part type, like part store peers.
So once you have your conclusion, how often do you need to update it?
This was one time case where we were replacing kind of one system with another system. So in that replacement, we had to prove to our executives that this new system that we're putting in place is actually will be doing better than the old system.
And then once the new system is in use, how often do they run the system to check?
So each time we produce a forecast, we do have like a dashboard which allows data scientists to look at that dashboard in order to see that everything's going on okay, this model's working properly. But we're not going into this kind of detailed analysis every time that we run it.
What is the sales forecast now? Is that a daily, weekly, monthly? How often do they update the sales?
Weekly.
Can you say what the model type was?
It's an ensemble model which uses linear regression and random forest.
Did you do any, there was a point where you showed the distribution, and of course you put a bell-shaped curve. It's not bell-shaped.
No, it's not.
Not by any means. Did you do any analysis to see if you could fit a standard distribution into the sales? I mean, log normal or something like that, exponential? Did the data for parts fit anything like that?
Even after log normal, even after log transform, it's not very normal, no.
So, you said that the system that you were using to do the modeling had a limit. What system were you using that had that limit?
It was a limit on that particular virtual machine on which we were running this.
Okay.
It's in terms of processing power, not in terms of actual data analysis problems.
In terms of memory, or I didn't know if you might have been using, R, jump, whatever, and it would have had a limit that I wasn't aware of.
No. It was like the processing power of the virtual machine.
Got a few questions from chat. The
Yes.
first one is, what is the frequency of replenishment from warehouse to stores?
It depends on the store. We have stores with different kind of schedule. Many of them are actually replenished overnight.
Okay. How do you reconcile the quantity for replenishment? Is it reconciled down or reconciled up, or?
This particular one is actually not reconciled.
Okay. Is seasonality of parts built into the forecast?
We do have several systems which require weekly forecasts, and for those we do produce seasonality. And if you have a yearly forecast and a seasonal indices, then you can produce weekly forecast by multiplying them.
Awesome. Those were the audience questions so far. So live studio audience, more questions, please. Another one. Did you have special models to predict the probability of the length of zeros?
I'm not sure I understand that question.
Looking for a clarification. I'm sure it's being typed. But I think possibly looking at, like, if you have a model which is almost entirely zero sales, where you mentioned, hey, it may sell in a year or a couple years. Was there a specific model for that, or was there just a general model for that, as well as the paper towels that sell 3 or 4 times a week?
So not for this particular model, but in other models we do use kind of 2-step modeling where we predict zeros first and then we predict everything else after. Yes, and it is useful.
That's kind of where I was going with the distribution, because I can see different parts having different distributions, and you need different models for, whatever it is.
Yeah, Steve brought up Poisson models as an example. So the probability of a non-zero incident occurring. So yeah.
Has there been any distribution, or is there a distribution where you'll take some very low probability items and put them in different stores, so that if somebody actually did need one, that these stores were close enough to each other that you could get a truck to bring it over, or send the customer to another local store?
Yep, we do that.
Okay. So it isn't just we're not going to stock it, but that's a special stocking consideration.
That was a good question. That was good. That made a lot of sense.
How do you take profitability into consideration? I think you have part A and part B. If part B is more profitable, how do you fit that in the model?
It's not in the forecasting model. It's like part of that assortment, which I told you that I'm showing you extremely simplified version of it. And the true version is much more complicated.
What was the question?
It's, yes, like,
So for the listeners.
oh, sorry. The question,
Oh,
okay, thanks.
okay, no problem.
Another question.
It wasn't as much on the data science piece. It was just, I was very surprised that the turnover was only 0.3. It's like, how do you maintain these chains with that low turnover? They charge you more. Yeah, margins on that, it has to be like crazy.
That's why we're the industry where data scientists are extremely important.
Or you go to the store and they say, we'll have it for you tomorrow, or the day after, because it's just not worth keeping in the store.
That happens if you have a 16-year-old vehicle. Probably will happen a lot.
Think about buying an engine block. How often do they sell a particular engine block, right? Those things aren't going to be in the store, right? Windshield wipers are great for them. Spark plugs are great for them.
You sell a lot more online than in stores.
We currently do not sell more online than in stores, but we have an online store, and we have we're second best in online sales after Amazon.
And you can pick up at your closest store.
And you can pick up at the closest store, yes.
Wait, are you the guys who have just started advertising? Call us by late in the afternoon, you'll have it by tomorrow?
I have not heard about that one, I'm sorry.
I just started seeing that advertisement on Netflix, on Roku, from one of the auto parts stores, and it was red and yellow, but there's 2 red and yellows. And, where they were saying, call us by this time in the afternoon for, on Friday, and we'll have it for your Saturday job. This thing about broken cars, people want instant gratification. They don't want to wait for that part for 2 days.
Still can.
They pull the parts for you, though. I'm not sure you go like,
LKQ.
yeah, okay.
Yeah, and depending on the part you're looking for.
Anything else online?
I would,
Oh yeah, go ahead.
why, how did you come up with the idea that you should challenge your model? And then how did you decide what to challenge it with, right? I mean,
So
in
our
other words, you did this test, you did this analysis, and somebody said, well, let's see if we can make a better model, a better predictor to save more money. And then you decided, somebody picked what things that they were going to compare against, right? Somebody picked new things.
So after this was done, every time that we went through any model improvement, our task was every time much easier because we were improving quantity model and comparing that to another quantity model. So there, we just had to agree on what kind of metric for quantity model we're using, and just show that according to the chosen metric, the new improved model is better than the old model.
But you had also said that your old model gave you assortment, but not replenishment. So I assume somebody said we also want replenishment.
Yes, but replenishment was already quantity-based forecast. So there we just compared two quantity-based forecasts, which was not that extremely interesting task.
Well, I'm impressed that how much advanced auto parts puts into deciding what goes on the shelf and what's stored. That's pretty impressive.
Well, I was going to ask, was this all done in-house, or did you contract it out? The statistics part.
At the time, we did work with contractors, but after that, we did expand our data science team, and now we do things like that in-house.
All right, thanks everybody in chat. We are gonna shut down the stream in just a moment here. Next month, we're gonna see how many of these we can stream, hopefully all 3, but stay tuned, meetup.com/trypass. Thanks for stopping in or for watching the recording after the fact. Goodbye now.